Hey guys, welcome to the second video on the acidity trends. So if you watched the last one, we left off with covering the atom factor in terms of acidity. So we're going to be covering the other ones today. And so if you look right at our little ARIO over here, ARIO mnemonic, resonance is the next one, okay? And so I numbered them in terms of priority, in terms of, and what that really means is, let's say they gave you three structures, right? If we can determine their acidity because the proton that we're deprotonating is all on different atoms, such as, like, let's say I gave you O, H, N, H, S, H. We can determine the acidity strictly based on looking at the atom. And so that is going to be the first thing you look at, and therefore if you can do it, if you can determine the acidity based on that and that alone, you can be done with the question. But if they gave you something like now where resonance can come into play like that, and so this oxygen atom right here and that one, the negative charge will form on the oxygen, and so we can't just look at the atom alone because it's the same atom. So when you cannot differentiate because of the first factor, you have to now move on to the second one. All right, so resonance is the first one we're going to be covering. So let's look at these two structures over here. All right. So we have this group over here, and if you're not sure what this group is called over here, it's called a carboxylic acid. Okay, when it's a carbon double bonded to an oxygen, and another bond to an OH group. All right, and here we have our alkoxide, as we saw similarly in the last problem. All right, and so first, when we're doing ARIO, let's just draw the conjugate base and try to look at the atom that's being deprotonated first. So here's a little base. Let's draw the arrows. And so to determine, we're going to look at the hydrogen that's being deprotonated. It's going to be this one, right? So we'll draw the conjugate base. Okay. So the first thing we always look at with ARIO is the atom that was just deprotonated. And so in this case, they're both oxygens. So since they're the same atom, we cannot use we cannot differentiate between them. The electronegativities are the same. And so we have to move on to the next factor, resonance. All right. And so remember that our whole job is to see which conjugate base is going to be the most stable, right? And we're dealing with electrons here. If we can spread out or delocalize electrons, then that delocalization allows us to, the spreading out of the electrons or delocalization means that they're going to be more stable since they're not tightly concentrated in one region. So if we can resonate that negative charge that we form because of that deprotonation, that can make it more that can make the original acid more acidic than one that cannot resonate. And so let's look at the resonance between the two conjugate bases now. All right. So if we look, we have this negative charge here with 3 lone pairs. And what we can do is we can resonate this to the carbonyl, right? And so we can take this one of these lone pairs, bring it down, and then we'd have to resonate that double bond up. So let's just draw the resonance structure. So we're going to have this, and now we have that. And so you see that this negative charge has now been spread out over a distance between that oxygen through that carbon into that other oxygen. Okay, so we can spread that negative charge out, and because it's not so tightly concentrated, it increases the stability of the conjugate base. Let's look at the structure on the right. So oxygen is connected to a carbon with 2 hydrogens, and also that other carbon over here. So in this case, we cannot resonate that oxygen, right? Because these 3 lone pairs, there's nowhere for it to go. If we tried to do that, it wouldn't work just because this carbon over here has already 4 single bonds and no MTP orbitals. All right? So We can't resonate in this case. So that means all those electrons are going to be confined to that one oxygen atom and are not going to be spread out. And so comparing these two conjugate bases now that we have here, this one is going to be more stable because we can delocalize the electrons, and this one is going to be less stable because we cannot delocalize the electrons. And so we need to, now to figure out which one is the more acidic, remember the basic principle is that the more stable your conjugate base is, the more readily your acid will give up a proton, which means it is more acidic. So which one is the more stable one? Well, we said it's going to be this one. And so that means by definition, this is going to be the more acidic compound. Okay? That's going to be the more acidic compound. Now we're going to move on to induction. Okay? So what induction is, you'll see most often halogen atoms are going to be on your compound, right? Halogens are that column with chlorine, bromine, and iodine. All right. And so what induction does is it utilizes the electronegativity of a halogen to stabilize a negative charge. Okay. So in this case, we're giving three compounds. All right, and they could do this on a test, and they'd ask you to order which one is the order the three compounds in terms of the more increasing acidity. Right. So you need to figure out which is the strongest acid, the weakest acid, and which one is in the middle of them. Okay. So the first step, ARIO again, draw the conjugate base and look at the acid. So we're going to do that first. So I'm going to draw a little base. And we're going to deprotonate. Okay. Alright, so there are three conjugate bases. So first let's look at the atom factor, right? The negative charge is always going to be on three oxygens in this case, so we can't differentiate strictly based on what atom was deprotonated. Now let's look at resonance, okay? And so we can take this and we can resonate here. We can do the exact same thing over there. And we can do the exact same resonance over here. And so none of these three compounds are different in terms of resonance. We can't differentiate strictly based on the atom and the resonance. And so now we're going to have to look at induction, okay? So I'm just going to delete these arrows over here. Okay? And so if we look, the compound on the left, does it have a halogen on it? No, it does not. So let's just write no halogen. Now let's look at the compound in the middle. Okay? So we do have a halogen on it, right? It's going to be coming off of this carbon right there. And so what this chlorine does, it's an electronegative atom, so it's going to be pulling electrons towards itself, right? So it's going to be kind of pulling electrons like that, all right? From this right side of the molecule to its left side. And so remember, we want to stabilize our conjugate base. One way we can stabilize it is by spreading the electrons out. And so we know that this can resonate, negative charge can resonate this way, like that. Another way that it's going to be stabilized is that chlorine is also going to be slightly pulling on those electrons toward itself. So it doesn't just confine it to the resonance stabilization. The chlorine can now pull some of those electrons towards itself. So it's not going to resonate to the chlorine. We can't because there's a hydrogen there, right? But it's going to still be able to pull off some of the density to itself, all right? And so that does offer a stabilizing effect. So if we're comparing these two molecules, because this one has no halogen that can pull those electrons towards itself, it's not going to be as stable as this one. So here, let's number these. I'm going to label this as number 1, number 2, number 3. And so between 1 and 2, structure 1 and 2, this one is going to be more stable than 1. I'm referring to the conjugate base when I talk about the stability. So let's look at the third compound, number 3. It can resonate the same exact way, we discussed that before, but it also has a halogen on it now. The difference between structure 2, the conjugate base of structure 2, and the conjugate base of structure 3 is the distance of that halogen. Here it was 1 atom away. Now it's going to be 1, 2, 3 carbons away. Okay? So it's further away from that negative charge. The thing about induction is if the effect falls off the further away your halogen is. And so our halogen here is 3 carbons away, so it's going to have a much weaker effect of pulling those electrons towards itself. Okay, so it's going to be much weaker in trying to pull those electrons towards itself, right? You just see I drew a little thin line to help illustrate that. And so that means that structure 3, the conjugate base of structure 3, is just not going to be as stable as, let's say, structure 2. And so not as stable as 2. And again, I'm referring to the conjugate base. And so let's summarize which of these 3 the stability of the conjugate bases. So the one on the left has no halogen. It has no offered stability by that halogen. It can resonate, and the negative charge is on the oxygen atom. All 3 share the same resonance and the same atom that's being deprotonated, so we are judging this solely on induction. So the one on the left has no induction. The one in the middle, the chlorine is very close, and so its induction is strong. And the one on the right, the chlorine is much farther away, and so the induction is weaker. So that means that the one in the middle is more stable than the other 2. The conjugate base is more stable than the other 2 because chlorine is closer, and it can exert a stronger effect, and a stronger inductive effect. The one on the right is going to be a little bit less stable than the middle structure because there is a chlorine there, so there is some inductive effect. It's just not going to be too strong. And then the one on the left is going to be the least stable simply because there is no induction period. All right? And so remember how we said that the stability of the conjugate base determines the acidity of the original acid? So if the middle structure is more stable, or number 2 is more stable, it's going to be the most acidic. So I'm going to put number 2 in front. The one on the right is going to be the second most stable, so it's the second most acidic. And then the one on the left is going to be the least stable, so it's going to be the least acidic. So acidity increases as we're going from left to right in the way that we ordered it. So that's definitely a common question they like to ask on the test. They will usually give you 3 compounds and ask you to arrange them in terms of acidity. I think there's something like that on the workshop. And so now let's move on to a special case. It's called competing resonance, okay? So this is something you have to watch out for. They could put it on a test. And so we're going to use ARIO again. And now you need to be careful about which hydrogen we're deprotonating, okay? When you have something like this where you have like that O and that CH3, we need to pick a hydrogen that's essentially in common with them, all right, because these structures are a little bit different from each other. And so you want to focus on kind of the hydrogen that is the same throughout. So you see how this oxygen has a CH3 group, whereas there's only one CH3 on the structure on the right. They're not going to be the same in that area. They will have a very common hydrogen right here. They both have that hydrogen right there. And so that's what we're going to focus on first, all right? So that's also what you want to look for when you're doing these questions, is which one they have in common. So let's draw a base. Okay. And now let's draw our deprotonation reaction, right? We're going to have hydrogen, and I'm just going to put it right onto the atom. Do not try to essentially skip ahead and try to do any resonance. Okay. And so these are our two conjugate bases. So let's look at the atom that they're on. The negative charge is on a carbon. Okay. So we can't differentiate between atoms because they're both on carbons, the same thing. So we have to go now to resonance. Okay. So the thing about the resonance here is, let's draw the arrows. We can take this negative charge, and if you want to pause here and try to draw it yourself, the resonance structures, feel free to do so. So on the left-hand side, we can draw this negative charge, forming a bond there, and that double bond is going to have to come up. Same for that one. So let's draw the resonance structures, actually. So we're going to have now this structure on the left-hand side, and on the right-hand side we're going to have this structure. Okay, so that's one resonance structure for each. The problem is the structure on the left has another good resonance structure. Okay, you see how we have that OCH3 group on the right side of this molecule? So here we go. I'm focusing over here. We have this OCH3. So that OCH3 is also capable of resonating. It can resonate to form another structure. So we're still left with that negative charge on the carbon on the left, but in this case, the OCH3 on the right side is participating in that resonance, another resonance structure. Okay, and so because that structure on the left, right, this structure on the left right here, all this part, can essentially, it has two good resonance structures, right? One where we're focusing on that carbon, the lone pair on the carbon resonating, and one where the OCH3 is resonating. It is now in a competition of which one is going to win. Is it going to be the left-hand side or the right-hand side? The thing about resonance structures is that they're in equilibrium with each other. So both of these could be existing in the solution or whatever at the same time, right? And so this competition, because that OCH3 is present, that negative charge in the carbon may not always be delocalized. Okay, may not always be delocalized. That means in some cases it could be confined to that one carbon. Whereas if we look at the structure on the right, that negative charge can always resonate to that oxygen. All right. And so because of this competition induced by that other OCH3 group, that carbon, and because that carbon now cannot always resonate to that oxygen, it is not going to be as stable on the left, this structure over here, conjugate base, as that one is on the right. Okay, so that's known as competing resonance. So when you're doing these questions, you need to watch out for if your compound may have a substituent that can resonate. So on the right we have a CH3 group. It's not going to be able to resonate, but the structure on the left does. That negative charge in the carbon is competing with that OCH3 for which one will form that double bond. All right, and so that's going to destabilize it a little bit. And on the right-hand side, it's going to be a little bit more stable. Okay? So that's why on the right-hand side, the conjugate base is going to be more stable on this compound than the conjugate base on the left-hand side. And so if we're talking about which one is now more acidic, it's going to be the structure on the right-hand side, right? Because the structure on the right-hand side's conjugate base is going to be more stable, and therefore the original acid is going to be more acidic. So now we have another case that we're going to work through. It's going to be about methyl groups. Okay? And so they're going to ask you which of these two compounds is going to be the more acidic ones. First thing you should do is ARIO again, draw the conjugate base. So here we have our base, here we have our base. And if you want to pause and figure out which hydrogen we're going to do, feel free to do so. And in this case, since we have the difference, the CH3 group is not the same as that H on the right hand side, we're going to look again at this hydrogen. Alright, and so let's draw our arrows. Okay, so these are our two conjugate bases. If we look at the atom, they're both on carbons, so we can't deduce anything in ARIO in terms of just looking at the atom alone. Now let's look at resonance. We can resonate that over here. You can do the same for the one on the right. If you want to draw those resonance structures just for practice, feel free to do so. I'm not going to do that. And so we can look at the resonance, but there is a factor here that does determine which is more acidic. That's the presence of that methyl group on the left-hand side of the left compound. So the thing about methyl groups is that they are known as electron donating groups. Okay, just as this OCH3 over here can resonate, can essentially donate electrons into the system and make this resonance structure over here, right? That OCH3, that oxygen there, donated electrons and made a double bond. The methyl is also known as an electron donating group. The only difference is it just cannot resonate. Okay, and so that methyl group is going to be donating electrons. All right, just as this carbon over here with that lone pair, that negative charge, will be donating electrons into here. So we now have, again, two things donating electrons. Okay, they're both going to be sort of competing. There's no competing resonance here, but there is some form of electron donation competition. All right, and so this is, you can think of it similar to competing resonance. Just make sure you know that it is not resonance. All right, so that because a methyl, or actually really not just methyls, but any of those carbon chains, you could replace that CH3 with an ethyl group or any other carbon chain. They're all known as electron donating groups. And so that's going to, if we look here, just know that this is not a resonance arrow that I'm drawing. It sort of pushes electrons that way. Just as this lone pair will donate electrons that way. Okay?